All right, if you've ever stared at a dense, textbook description of physical layer protocols and literally felt your eyes glaze over, well, you're in the right place. Welcome to this explainer. Today, we're breaking down one of the most clever tricks in data transmission. We're going to tackle the physical layer, specifically zeroing in on a brilliant coding scheme that solves a massive, real-world problem in networking engineering. And I promise you, by the time we wrap up here, this whole complex protocol is going to make complete logical sense.
So, here's the ultimate engineering pain point. We constantly want to push more data faster across our copper wires, right? But physical cables have strict bandwidth limits. High-frequency signals degrade, they cause electromagnetic interference, and honestly, they're just incredibly difficult to manage. So the million-dollar question is, how on earth do we transmit more data without just stubbornly doubling our signal bandwidth? Well, the secret actually lies in changing how we encode the ones and zeros onto the wire in the first place.
Enter our solution, MLT3. Now that stands for multi-level transmission encoding with 3 levels. Unlike your standard, simple binary codes that just flip back and forth between a high and a low voltage, a simple 1 or a 0, MLT3 introduces a third state. It uses 3 distinct voltage levels, positive, 0, and negative. By shifting from a binary signal to this ternary signal, we unlock some absolutely incredible efficiencies. But to really grasp how it works, we first got to understand the rules of how it moves between these 3 levels.
To make this stick, I want you to imagine a visual analogy that you'll never forget. Think of MLT3 as an elevator in a really short 3-story building. You've got the top floor, which represents our positive voltage, you've got the lobby, which is our 0 voltage line, and then you have the basement, which is our negative voltage. This elevator is the signal on our wire, and the data bits we want to send, our ones and zeros, those are basically the buttons telling the elevator exactly what to do.
All right, so here are the absolute mathematical rules of the MLT3 elevator. They're strict, but honestly, super simple. Rule number 1, if the input data is a binary 1, the elevator must move to the next floor in its sequence. So a binary 1 forces a voltage level change. Rule number 2, if the input data is a binary 0, the elevator stays exactly where it is. It holds its current voltage level perfectly constant until the next one comes along. Basically, 1 means move and 0 means hold.
But wait a second, where does the elevator actually go when it moves? It can't just jump around randomly, right? It has to strictly follow this exact sequence loop. It goes from the lobby, up to the top floor, back down to the lobby, down to the basement, and then back to the lobby again. Mathematically, that's 0, then positive, then 0, then negative, over and over again. It never, ever skips a state. So if you're at positive, your next move on a binary 1 is always going to be back to 0.
Now, check out the massive advantage this ternary logic gives us. When you compare standard non-return to 0, or NRZ coding, with MLT3, the difference is just staggering. Because MLT3 cycles through 3 levels and only changes state on a binary 1, it needs way fewer voltage transitions to send the exact same amount of data. The reference material actually states this explicitly. MLT3 transmits 1 symbol per bit, but it requires exactly half the bandwidth compared to NRZ. Half! I mean, that is a huge win for signal integrity and cutting down on electromagnetic interference.
Okay, theory is great, but as engineers, we really need to see this working on the wire. So we're going to trace the digital signal using this exact data string taken straight from our source text 010011101101. We're going to feed this string right into our MLT3 elevator and see exactly what the voltage output actually looks like.
Let's methodically solve the first few bits together. We'll start our elevator right in the lobby, at level 0. Our first bit is a 0, and remember the rule for 0? It's hold, so we stay at 0. The next bit is a 1. The rule for 1 is move to the next state, while the next state after 0 is positive. Following that, we get 2 zeros in a row. So what do? We hold. The voltage just stays flat at positive for both of those clock cycles. Then bam, we get another 1. The rule is move. The next state in the sequence after positive is right back to 0.
And this brilliantly illustrates the exact result you'd get on an oscilloscope. With our data string running, the MLT3 ternary waveform reacts directly to it. Just think about that middle section where we have 3 ones in a row. The signal goes from 0, down to negative, back up to 0, and then up to positive. It is strictly following that 0, negative, 0, positive loop because every single one is forcing a state change. And whenever there's a 0 in the data stream, the waveform is perfectly flat. It just holds its state. Now, as any good engineer knows, you always have to test the edge cases, right? So let's shift gears for a second and look at a potential pitfall. I want you to think about this critical troubleshooting question. We know that a binary 0 means our MLT3 elevator holds its state. But what happens if the incoming data stream is a massive, long string of continuous zeros? Does our elevator just get stuck in the lobby forever? What does the physical signal look like then?
Well, if we have a long string of zeros, the voltage line just goes flat, and it stays flat. It doesn't move at all. And this brings us to a fatal flaw in the protocol. The text highlights this explicitly, stating that clock recovery is not possible. You see, receivers actually use those transitions, the moving edges of a signal, to synchronize their internal clocks with the sender. So, if the line is just a flat voltage for a long stretch of time, the receiver entirely loses track of where one bit ends and the next one begins. It literally loses the clock.
So the crucial takeaway here is that because of this flatline trap with continuous zeros, MLT3 just cannot survive on its own. The source text makes it clear that MLT3 must be combined with a second coding method. Usually before the data is even handed over to the MLT3 encoder, it runs through a secondary block code, something like 4B5B, which mathematically scrambles the data to guarantee that there will never be too many zeros in a row. Basically, MLT3 gives us the amazing bandwidth reduction, but it totally relies on a partner code to keep the clock ticking.
Okay, let's lock this in. Here is your rapid-fire recap of the 3 most critical takeaways. Number 1, MLT3 uses a ternary signal, that's our elevator of positive, 0, and negative. It loops to the next state on a binary 1 and holds its state on a binary 0. Number 2, the massive benefit here is that it cuts bandwidth requirements exactly in half compared to standard NRZ coding. And number 3, the fatal flaw is that it has no inherent clock recovery. If you send too many zeros, the signal flatlines, meaning it absolutely must be paired with a secondary code.
And there you have it. You have successfully decoded MLT3. You know, the physical layer is really just an endless game of engineering trade-offs, sacrificing one luxury, like clock recovery, to gain a massive advantage in bandwidth. It kind of makes you wonder, as our data demands literally double every few years, what physical limits are we going to have to cheat next? If you found this explainer valuable, make sure to subscribe for more communication system survival guides. Keep learning, and I'll see you in the next explainer.